Okay, so section 5.6, the goal is here to learn the meaning of two different theorems. One is called the remainder theorem, the other is called the factor theorem, and this will help us to simplify different polynomials and solve them. So first of all, something kind of interesting, something involving a topic we talked about earlier. It's called synthetic division. And we just want to see here what's going to happen if, first of all, on the left side we evaluate f of 3. So f of 3 means in this equation up here, f of x, wherever you see an x, you will now plug in the number 3. That's what this means. F of 3 just means plug in 3 for x. It's a shorthand way of saying that. So there's an x in this equation, so I plug in 3. Here's another x. When you solve that, you're going to get negative 3 times 3 squared is 9, negative 27, plus 5 times 3 is 15, plus 4. And this whole thing comes out to be negative 8. Okay, so let's sidebar that for a sec. On the other side, we want to now divide f of x by this right here, and we'll use synthetic division. And one thing I want to point out, think about dividing by x minus 3, think about what would make that expression equal to 0. And the answer is 3. So that's how we start our synthetic division. This right here represents x minus 3. It's positive 3 instead of negative 3 because positive 3 is what makes that 0. How do we get the rest of the numbers? Well, we're going to use these coefficients. Negative 3, 5, and 4 we go here, here, and here. Remember, synthetic division, we can do it when it's x to the first power, which in this case it is. So that negative 3 represents x squared. That represents x. What we do with synthetic division is we add the columns. Since there's nothing under the negative 3, that's like a 0. And then we multiply these numbers. Negative 3 times 3 is negative 9. 5 plus negative 9 is negative 4. We're going to multiply negative 4 times 3. We get negative 12. 4 plus negative 12, that's our remainder, negative 8. Notice that negative 8 is the same thing we got over here. So that is part of what we're talking about right here. That's essentially an example of the remainder theorem. The remainder theorem says that if you plug in 3 to this function right here, that is the exact same as if you get as your remainder when you divide it by x minus 3. So for example, if I did f of 4, that would be the same as dividing it by x minus 4. If I did f of 10, I'm going to get that the same number as my remainder if I divide it by x minus 10. That's the remainder theorem right there. That's basically what it means. Okay, and this is another way of saying the same thing. So if this looks confusing, I just put some numbers here. 14 divided by 6, that's, well, 6 goes into 14 2 times, and it gives you a remainder of 2 over 6. Okay, another way of saying that, if I just write this out, 14 over 6 equals 2 plus 2 over 6 plus remainder 2 over 6. Another way of saying that, if you multiplied both sides by 6, these would cancel, so we get 14, and that's going to equal, if we distribute, it's going to equal 6 times 2 plus, and then these cancel, leaving you with 2. Okay, that's just to show you kind of the pattern of how it works with numbers. This is what this stuff means up here. It basically means if you take a dividend, a polynomial that you're dividing something by, that's going to equal what you divided it by. Okay, what you divided it by, so, which is the divisor, times your answer. The quotient means the answer to the division problem, and then plus the remainder. Okay, so here's an example. If you take this polynomial and you divide it by x plus 10, you would get x minus 4 with that remainder. So if you wanted to put it back together, you could multiply these together and add 42, and that would take you back to your original polynomial. So let's do a couple examples. Okay, we want to do this by synthetic substitution and direct substitution. Let's do direct substitution first. Okay, direct substitution just means plug in 4, find f of 4. I'm going to test to see if this gives us the same thing as it does when we do synthetic division, because that's what the remainder theorem says. Okay, so 4 to the 4th is 256 times 3 is 768. 4 to the 3rd is 64 times negative 2 is negative 128. 5 times 4 is 20. And when we add these together, that's going to be 768 minus 128 is 640 plus 20 plus 2 would be 662. So here's what the remainder theorem says. The remainder theorem says if we now synthetic division, if we do synthetic division on this, and we do it with x minus this number right here, we should get a remainder of 662. So let's check to see if that happens. Again, this 4 represents x minus 4. That's the 4 is what makes x minus 4 0. These numbers right here should be the coefficients for each of these powers. And by the way, something important to note, we skipped a power here. There is no x squared, but we need to include it in order to get this to work. So there, in that original, there's 3x to the 4th, there's negative 2x cubed, there's 0x squared, but we still have to include it. There's 5x, and there's 2 for the constant term. We start by adding 3 to nothing, because there's nothing there. 3 times 4 is 12. We're always adding these columns, so negative 2 plus 12 is 10. 10 times 4 would be 40. We add those to get 40. 40 times 4 is 160. We add those to get 165. And 165 times 4 is 660. And we add those, we get 662. And that's our remainder. And that's the same as what we got when we plugged in 4. That is essentially what the remainder theorem says. Okay. Last thing, this is a pretty short section. Last thing is we want to talk about factoring polynomials and how to do that using synthetic division. Okay. So basically, we've kind of already done this. You may have noticed, like on this equation right here, if we're dividing this right here, we end up getting what's called a depressed polynomial. And depressed doesn't mean that the polynomial is sad or anything. It basically means that you're dividing each of these exponents by something that represents x to the first. And if you divide x cubed by x to the first, you get x squared. This number has been depressed by 1 from x cubed. You divide this x squared by x to the first, you get x to the first. It's been depressed from x to the second down to x to the first. Finally, if you divide x to the first by x, you just get nothing in terms of the x. It's x to the 0. That's what we mean by a polynomial. And now what we can say is we can say this thing that we ended up with, remember before when we did 6 going into 14, and we got remainder 2. We got 2 remainder 2. Another way of saying that is 2 times 6 plus the remainder is equal to 14. So now we can do the same thing with the polynomial. We can say this thing right here times what we divided by times x plus 3. So 2x squared minus 9x plus 10 times x plus 3 plus the remainder in this case is 0, should equal what we originally divided by, should equal that. And it does if you check. If you multiply that out, it does come out to be that original cubic polynomial. Okay, so let's talk about this now, the factor theorem. This basically says that if you divide something synthetically and you get a remainder of 0, that means that whatever you divided by, in this case we divided by x plus 3, whatever you divided by is a factor or can be evenly factored out of that original polynomial. Okay? So this is what this says. This says if x, for example, if x minus 2 is a factor, okay, it is a factor if when I do synthetic division with 2, if I synthetically divide that, I end up with remainder 0. That's what the factor theorem says. This will be clearer when we do an example, so let's do one right now. So this says determine whether x minus 5 is a factor. Well, how will we know if it is? We'll know if when we do synthetic division, we wind up with remainder 0 right here. We want to get a remainder of 0, so let's see if that happens. First of all, x minus 5, if I'm synthetically dividing, I need to put a 5 there, because 5 is what makes x minus 5 0. Okay, then we're going, let's make sure we don't skip any powers. We go x cubed, x squared, x to the first, x to the 0. So all the powers are there. These numbers are the coefficients. 1 is here, negative 7, positive 7, and 15. And we do the synthetic division. We're adding the columns and we're multiplying by those numbers. 1 times 5, we add those to get negative 2. Negative 2 times 5 is negative 10. We add those to get negative 3. Negative 3 times 5 would be negative 15. And when we add those, we do get remainder 0. That means that x minus 5 is a factor. Down here we also get a depressed polynomial, so this was x cubed. Since we divide it by x to the first, that means that's going to be x squared. This was x squared, which means down here it's x to the first. this is x to the first, which means down here we don't have an x at all. So now how would we write this? We could say that we've now factored this original thing to be this. We factored it to be x minus 5 times this thing right here. That's what's left over. And now we can factor, once you get down to the point where it's just x to the second, you can now usually factor it with techniques we used before. So now we want to find numbers that multiply to -3, add to -2. If they multiply to a negative, one has to be positive, one negative. And so only 3 times 1 equals 3. And it would have to be -3 and positive 1 to be able to factor. And that's exactly what it is. So that's the factor theorem. It says if you do synthetic division getting a remainder of 0, you just found a factor of that original polynomial. And usually you're going to get a second degree where you can use the quadratic factoring that we've done earlier. Okay, so that's section 5.6 on the remainder theorem and the factor theorem.